recording. So, okay, as we've discussed, we're going to talk about transformations of functions. A good website to go to and to see the actual functions that you're graphing is www.desmos.com. And so today we want to learn about shifting graphs vertically and horizontally, reflecting graphs, stretching graphs vertically and horizontally, and order of transformations. So every boxed information, piece of information, put it on a sheet of paper. It's important. Review it when? How often? Daily. Good. All right, so horizontal shifting and translation. Let f of x be a function and let h be a fixed real number. If we replace x with x minus h, we have a new function. That new function is g of x equals f of x minus h. The graph of g has the same shape as the graph of f, but is shifted h units to the right if h is positive, and shifted h units to the left if h is negative. So let's read that again. That new function is f of x minus h. That's the new function. The graph of g has the same shape as the graph of f, but is shifted h units to the right if h is greater than 0. And is shifted what?
H units to the left if h is less than 0.
Good, if h is less than 0 or negative, right? So what does that mean? If h is negative, it's really going to be like x plus h. Okay? So let's look at a couple of examples.
Can you do the yellow in a darker color, please?
Yes. The question was, can we do yellow in a darker color? Yes. So we'll highlight it in black. You're welcome. Okay, so here we want to sketch the graphs of the following functions. Our first one is f of x equals the quantity x plus 2 cubed. What function stands out the most if we ignore the x plus 2? The cubed part, which you learned about in 4.4. X cubed. What's the shape of x cubed? Draw it in the air for me. I'm going to count to 3. And when I get to 3, I want you to draw it in the air. All right, so we just discussed that the shape of x plus 2 cubed, it has the same shape of x cubed, but because it has an x plus 2, are we going to the right or to the left?
To the right.
I heard to the right, I heard to the left. What does that mean? It's going to the left. Good. Because that means h is negative. Because it's the opposite of what you think. Right? Because it's on the inside. So if it were x minus 2, it would look just like that. And then you go to the right. Right? Because that h will be positive. But because the sign is the opposite, that really looks like x minus negative 2 cubed. So that means our h is negative 2, which is less than 0. So that means we take the graph and we go to the left 2. What questions do you have? Okay, so I'm going to pause the video. And so let's make our graph a little bit more accurate, because we know we have a y-intercept here. So if you want to find your y-intercept, how do you find that? How do you find your y-intercept? Good, you set x equal to 0. So when you set x equal to 0, okay, so when you set x equal to 0, that gives us y equals 0 plus 2 cubed, which means y is 2 cubed, or y is what? 8. So that means this point here is 0, 8. Okay? So that's how we made our graph more accurate. What questions do you have? Okay, so that is x plus 2 cubed. quantity cubed. Now, take a minute and graph g of x equals the absolute value of x minus 4. What do you think is going to happen? I'm going to give you time to graph it, but I'm just asking you, what do you think? Go ahead.
I forgot what it's called. You know how in the other one's parentheses?
Yeah.
And it's like do it change how the graph is? Or
The shape? So you're asking, does the shape change? Yeah. What is the shape for, well, I'm going to ask you guiding questions. What is your dominating function here? What's the function that stands out? X minus 4?
G of x? Oh.
What is the outermost function? How do we read that function? How do we read this function?
G of x equals the absolute value is x minus 4.
So what's the dominating function? The absolute value, right? Good. What's the shape of the absolute value? I see hands in the air. Does everybody agree?
So I have a question.
Wait a minute. Let's get that first. Does everybody agree with that part? Or is your question based on does everybody agree? Does everybody agree on that? So it's a V.
Yeah.
That's the absolute value function. Okay? And now I'm going to give you a chance to graph it. What was your question?
So if it's a negative 4 right now, and then we do it in the absolute values, it would be a positive 4. So then we do
No, because it's absolute value of x minus 4. It's not, this is not the same thing as the absolute value of x minus 4.
So
They don't say do the same thing.
So would it change to x plus 4?
No, because these two things are not the same. Whenever you have the absolute value of x minus 4, this is one expression on the inside. What you're thinking mentally is you're taking the absolute value of x and separating it, and taking the absolute value of negative 4 and separating it. But that's not what we do for this particular function.
So how would we do the opposite like we do on the
That's what I'm asking you. That's what I'm asking you right now. I'm asking you, given the absolute value of x minus 4, how do you graph it? What's the shape? That's what I'm asking you. I'm asking you how is this really impacting the graph of the absolute value of x? What type of transformation is happening?
A shift?
Yep, it is. It's a shift.
It's like a.
How do you graph this? It's a V, yes. I see hands. It's a V, but describe it in terms of shifts.
To the right 4.
Shift to the right 4. Do we have a y-intercept? And if we do, what is it? It's at 4, right? Good. How do you find it if you need it? Set x equal to 0 and you solve, right? Good. Very good. So we have a horizontal shift of the absolute value to the right 4, right? Because here, if you want to find your y-intercept, you set x equal to 0, and you get y is equal to the absolute value of negative of 0 minus 4, and that's the absolute value of negative 4, which is 4. So that's how we got our y-intercept there. Okay? Very good. All right? So we know how to understand horizontal shifts. Okay? It's important to remember the rules. Did everyone have that?
Yes.
See some still writing. Okay? Then you should have, it'll be on the inside, right? If you had a horizontal shift, that would have been the absolute value of x minus 5. So if you combine them now, if you have 5 times the absolute value of x minus 5, that says go to the right 5 units and then stretch that by 5.
Okay.
Does that make sense?
Mm-hmm. So what if it was a 5 absolute value of negative x? How would that be graphed?
So you graph the absolute value of negative x. What does that look like?
Split
A flip across.
Downward.
Across, you got. I'm giving you the words you got to use. Yes, you are absolutely correct when you say a shift. But did you say shift? What word did you use?
Flip.
I said downward.
You flip. So a reflection.
Yes.
Reflection. Reflection about what?
X-axis.
About the x-axis. So it's a downward V, and then you stretch it by 5. Good. Very good. So, when you see x plus h, you should think of that as x minus the negative h, as we pointed out previously. Okay? Now let's talk about vertical shifting and translation. Before we talked about what kind of shifting and translation? Horizontal, good. Good. So now let's talk about a vertical shift and translation. So let f of x be a function whose graph is known, meaning you know the graph of that function, and let k be a fixed real number. The graph of g of x equals f of x plus k is the same shape as the graph of f, but is shifted k units up if k is positive or greater than 0, and k units down if k is less than 0 or negative. Okay? So now it looks like your k is on the outside. Okay? So that's important to note. Vertical shifts, you have that constant on the outside. That's important. So with the vertical shift, you have the graph of f of x given. And so you have g of x is equal to f of x plus k. It's the same shape as the graph of f. That's important. It's the same shape, but it's shifted k units up if k is greater than 0, and k units down if k is less than 0. Okay? So 1 over x. Oh, there's a question.
If would there ever be like a problem where we would have to do both horizontal and vertical?
Oh yeah. Yes. Absolutely. We'll see some of those at the end of this section. Absolutely. Right now, I'm breaking it apart because you're just learning it. But yeah, we do combinations. Absolutely.
Oh my God.
So, example 2, we want to sketch the graphs of the following functions. One function I didn't ask you about, but you reviewed in 4.4 as well, was 1 over x. So Ashton drew the graph of 1 over x earlier whenever we were talking about the square root of x in the air. Who's Ashton? We learning people. That's what she's like, dog, why you do that? Like, why did you do that? It's a learning game. See, that's the point. You want to get to know your classmates. You want to see what's happening here. Okay? So let's talk about that. The shape of the graph of 1 over x, as she drew earlier, looks like this. Well, doesn't touch it. That you learned in 4.4, right?
Yeah.
That is the graph of 1 over x. So now f of x is equal to 1 over x plus 3. So what type of shift do we have? Vertical shift. Very good. Go describe what happens to me. It goes up 3, right? So if we take this graph, move it up 3, then what will it never touch?
The y-axis.
It will never touch the y-axis? What else will it never touch?
The x-axis.
What's the 3?
It will never touch 3. I heard the x-axis or 3, but if you're shifting it up, if you're taking this graph and you shift it up, what's happening is your line y equals 3 becomes your new x-axis, right?
Yeah.
And so we have to make adjustments accordingly. This is a sketch. And you have this. So again, you said it never touches the y-axis, and the x-axis, it now touches because your new x-axis became y equals 3.
Okay.
Does that make sense?
Mm-hmm.
And you can check it on Desmos. Would you like to check it on Desmos?
Yeah.
Okay, I'll give you a minute to do so. Very good. So you had time to check it. And we even talked about how you find your x-intercept if you need it. Remember you said y equal to 0. So to find your x-intercept for confirmation, you set y equal to 0, or your f of x equal to 0. So you'd have 0 equals 1 over x plus 3. And you get negative 3 equals 1 over x. That's really negative 3 over 1. You cross multiply to get negative 3x equals 1, or x equals negative 1/3, dividing both sides by negative 3. So we know that's negative 1/3. Okay? Very good. Other functions you learned about in 4.4. One was the cube root of x. You remember the shape of the cube root of x? Do it again. I see x cubed, and then I see it laying on the side. I see x cubed laying on the side. That's really x cubed laying on the side, right?
Yeah.
So it looks like,
It's like, is it?
oh, it's holding on. It's optimizing.
Narrow? Like, never mind. What's up?
It's like that. No, don't stop talking. That's the part of being in class and being engaged. That's x cubed. That's not x cubed. That's the cube root of x. This is the cube root of x, right? That's the cube root of x. Okay, that's important. So notice that what did we do immediately? We looked at our function. We saw it's g of x equals what?
The cube root of x minus 2.
And we automatically identified the dominating, or the function that stands out the most, right? That function was, we say our original function. Our original function was the cube root of x. Now tell me what you're going to do with the cube root of x.
Shift it down to.
Shift it down to? I see heads nodding, yeah? That's what we're going to do. We're going to take it and we're going to shift it down to. Are you going to have an intercept in this case?
Yeah.
An x-intercept, y-intercept? Do you need a second?
Both.
Both?
I lied.
I'll give you time.
This is not your
Cube root of x minus 2.
Sorry.
Cube root of x minus 2. Cube root of x minus 2. So here you take the cube root of x and you do what?
Shift it downward.
Shift it down how many?
2.
2. So it's a vertical shift
Yes,
down.
X and a Y intercept.
So it does have an x and a y intercept. That's what you had to check. And that's what it looks like, roughly. So you could find your x and your y intercept. You know how to do that. You know how to do that. To find your x-intercept, you set y equal to 0 and solve. And to find your y-intercept, you set, did I just say y-intercept or x?
You said what?
I say you find your y-intercept, you set x equal to 0 and solve. To find your x-intercept, you set what?
Oh, you said
You set y equal to 0 and solve. Good. Okay? It's a sketch. Let's go back. So if you have a horizontal shift, all right. Now let's talk about reflecting with respect to the axes. We have reflections. Okay, these are important as well. So far you have how many boxes?
3.
3. 3. Make sure you go over them daily and make sure you know them. Okay, so reflecting with respect to the axes. So given a function of x, f of x, the graph of the function g of x equals negative f of x, which is really like negative 1 times f of x. This is the reflection of the original graph with respect to the x-axis, okay? With respect to the x-axis. Are we clear?
Yeah.
So it's like you take it and flip it over to x. That's what this does. So given f of x, the graph of g of x equals negative f of x is a reflection of the graph of f with respect to the x-axis. Okay? Given f of x. Now notice that that first negative was on the outside. This one is where?
Inside.
On the inside. Okay? Good. So here, the graph of g of x equals f of negative x. G of x equals f of negative x is the reflection of the graph of f with respect to what axis? The y-axis. Very good. Okay? So let's look at a couple of examples. Here, well, would you like a minute to try both of them?
No.
No? Okay. So so in A we have f of x equals negative x squared. What function do you think about immediately?
X squared.
X squared. X squared. Very good. So we think about x squared. We know its graph is a?
Parabola.
Give me more. What about it? It faces up or down. Which one? Go ahead.
Is it down?
Well, x squared.
Oh, X squared.
Up. Very good. Very good. X squared faces up. That's the function you think about immediately. But as Jordan, right?
Yes.
As Jordan was saying, the negative x squared does what to it? Flips it. You got it. Very good. That's your graph.
Oh.
That's the reflection across the x-axis, right? Because the negative is on the outside.
So say if you put this on this exams,
Not on exams. Just ask your question.
or okay, so say you put it on, if you put it on,
Go ahead. Just ask.
would you just ask us to explain since
No, I can ask you the graph. Everything is fair game. Everything is fair game. I'm saying I could. So it sounds like your question is similar to the question that was asked earlier. Like, what types of things would you ask? I could ask you to describe it. I can ask you to graph it. I can ask you to sketch the graph. I can ask you to describe the transformations that are happening here. There are different ways of phrasing it to check for understanding without using a calculator, even if I allow you to use a calculator. That's the point I was making. Does that make sense? Did I answer your question? Okay, cool. Yes?
So when you reflect, it's gonna be like the same thing across the x-axis?
When that negative is on the outside.
Alright, so same for the next problem.
Let's do the next. Okay, any questions about the part A? Okay, let's move on to part B. Part B, you have g of x equals the square root of negative x. What function stands out to you?
That one.
That one. No.
Oh.
Yeah, the square root of x. You were pointing on the board. It's that
Was I
one.
right?
Yes, it's that one on the board that we labeled as the square root of x. You asked for a recording, so I'm trying to actually be more descriptive as well here. So when you watch this later, you can have it to reflect on. Reflect. Okay. Hey, and did, boo, and did. So you have g of x equals the square root of negative x.
I'm missing.
What do you expect to happen here?
Isn't it
it's
like
gonna
flip
go down,
this
like,
way.
it's gonna be
I heard it's gonna go down. I heard it's gonna.
like it's gonna
Down to the left.
It's gonna flip over the.
down to the
I
left?
see a different graph.
Oh, I'm on the wrong graph. I think
This is the square root of x. This is the square root of x.
Okay, so you're gonna take the thing and you're gonna pancake it and it's gonna go down like that.
No. That's
Down
flipping
to the
over the
left.
x.
Or it's gonna flip
Down to the
It flips over to y. Why does it flip over to y?
Because the negative was in the
You just know. I have no idea, but I know it's gonna flip over to y. Tell me based on the box we just discussed.
If the negative is in the parentheses.
Oh yeah. And it's a good thing. Your intuition is spot on. That's a good thing. Your intuition is spot on because you said flip it around to y. But mathematically, the reason we flip it around that y is because that negative x is on the inside.
Oh.
So we take this graph here, and then we flip it over the y axis, and it looks like that.
So say if it was negative square root of x, it would go like this.
That's right. If it were negative, if we change the function function and had negative square root of x, then yes, you are correct. You would take that and you flip it over like that. Does the difference make sense?
Mm-hmm.
What questions do you have? Okay, so let's talk about vertical stretching and compressing. Let's talk about vertical stretching and compressing. So in terms of a vertical stretch and a compress, let's just talk about it before we even go through the box. How many boxes do you have now? 4. Okay, so if you take something, think of a rubber band. If you take a rubber band and you stretch it, what happens to it? Describe what's happening.
It
It gets
elongates.
narrow.
It gets narrow and long. Okay? That's what's going to happen whenever you take your graphs and you do a vertical stretch. It's going to get narrow and long. Okay? But if you take that rubber band, you're still holding it on both ends in its original state, and then you press it, what's going to happen? It's going to get wider and shorter, right? So that's what you expect to happen. That's what you expect to happen. Now let's put it together with what's happening mathematically, okay? So let f of x be a function and let a be a positive real number. The graph of the function g of x equals a times f of x is stretched vertically compared to the graph of f by a factor of a if a is greater than 1. So what do we need to highlight here? If we have the parent function, f of x, then the graph of g of x equals a times f of x. Notice that the a is on the outside no matter what in this case whenever you do a vertical stretching or compressing. It's whether your a is greater than 1 or less than 1. Oh, come on. Okay, it's stretched vertically. Okay, the graph of the function g of x equals a times f of x is stretched vertically compared to the graph of f by a factor of a. By a factor of a if a is greater than 1. Okay? If you have the parent function f of x, then the graph of g of x equals a times f of x, that is compressed vertically compared to the graph of f by a factor of a if a is between 0 and 1. So if a is between 0 and 1, like a half, a fourth, 1/8, then you're going to do a vertical compression. If a is greater than 1, it's a vertical stretch of whatever parent function you had. So you have f of x equals the square root of x over 10. What's your parent function? F of x equals what? Square root of x. Good. So f of x equals the square root of x. So we think of that. And what do you do with that? Because see, notice the square root of x over 10 is the same thing as 1 over 10 times the square root of x. That observation you would have to be able to make on your own.
You stretch it.
Stretch it vertically, you said?
Compress.
We compress vertically? How many say compress vertically or compress vertically? Raise your hand. How many say stretch vertically?
Stretch it.
How many don't know? Okay, so let's go back up. So let's have a quick discussion. Here it says we do a what? A stretch vertically if what?
A is greater than 1.
So we should ask ourselves what is what? What is A? So for us, what is A? A is 10?
1/10.
Ah, A is equal to 1 over 10.
A is whatever that's in before the X.
Right. And technically right here you have a 1.
Yeah.
So it's not just the X, it's the square root of X here. So whatever's before the square root of X. So it's before that, which is 1/10. But if I give it to you in the format of square root of X over 10, you still have to be able to identify that your A is 1/10. Does that make sense?
Yes.
Okay, so we ruled out part 1 because we know A is 1/10. 1/10 is not greater than 1. Let's confirm. 1/10 is between 0 and 1. So that means we do a what?
Compress.
That's right, compress vertically. You need that vertically compressed. So if you take the square root of X and do a vertical compression, it's like you're putting a weight on top of this and pressing it by 1/10. So it's flat, a lot flatter. Okay, very good. Tell me what happens in B. Read B to me.
G of X equals 5.
Very good. G of X equals 5 times the absolute value of X. Go ahead, I'm listening. Teach me. What should you identify first?
The absolute value.
Your parent function? What's the absolute value? So what's the shape of your graph? You're teaching me. It's a V. Good. It's a V. It's gonna stretch. Stretch how?
Become
Narrower, right? Becomes narrower. So it's a vertical stretch. It's a vertical stretch. Becomes narrower. Very good. Vertical stretch by how many? Good. What questions do you have? Yeah, go ahead.
You would, like, if you was to have that drawn already, you would ask us to describe it, and what you just wrote is what we would describe.
That's possible, yes.
It's like everything's possible.
It's possible. I'm answering that question.
Like, are trying to articulate.
Yeah, that's good. That's good. You're describing what's happening. That's exactly what's happening.
Oh, it's cold.
Okay, you ready?
I also have a question.
Go ahead.
How come it wasn't, like, shifted? Like,
Shifted, what you mean? Shifted where?
shifted-
So now you have to use all your words, because when you talk about shifts, what kind of shifts exist?
Horizontal and vertical.
Right, so tell me about your shifts. What's your question now? How do you,
How come it wasn't a horizontal shift to the left because of the 5 minutes under the absolute values? Okay.
say it again? A horizontal, you saying why wasn't it a horizontal shift?
Yes, ma'am.
Okay, so the rest of this section is really adding on this. I'm going to pause here because I'm going to pass your exams back. All right, so now let's talk about horizontal stretching and compressing. Let f of x be a function and let a be a positive real number. The graph of the function g of x equals f of a times x is stretched horizontally compared to the graph of f by a factor of 1 over a, if a is between 0 and 1. So here we have if g of x is equal to f of a times x, this is stretched horizontally compared to the graph of f by a factor of 1 over a as long as a is between 0 and 1. The graph of the function g of x equals f of a times x is compressed horizontally compared to the graph of f by a factor of 1 over a if a is greater than 1. So let's look at an example. Let's sketch the graph of f of x equals x over 3 quantity cubed. So notice that we can rewrite this function f of x as the quantity 1 over 3 times x quantity cubed. Okay, so whenever we look at our function, notice that our a here is 1 over 3. So we're just making some observations. So note a is equal to 1 over 3. So what case are we in? We look back up. A is 1 over 3. Notice that in this case, a is between 0 and 1. So now what we do is we notice that our function is going to be stretched horizontally compared to the graph of the original function f. So what we're doing is really we're taking what's our dominating function, we're cubing it. So we're taking x cubed and we're stretching it horizontally like a rubber band. So just an observation. So this implies we're in part 1, and this implies f of x is stretched out compared to x cubed by a factor of 1 over 1/3, right? Because our a is 1/3, so we have 1 over 1/3, which is equal to 3. So, for example, we know that the point 1, 1 is on the graph of x cubed, and that will correspond to, and since we're stretching this horizontally, the only thing that's going to be impacted by that stretch horizontally is the x coordinate. So we get 3, 1 on the graph of x over 3 quantity cubed. So the graph looks similar to x cubed, but is stretched out a little bit. Okay? All right, excellent. So one more concept. So now we can talk about order of transformations. So if a function g has been constructed from a simpler function f through a number of transformations, g can be understood by looking for transformations in the following order. You have horizontal shifts, you have horizontal and vertical stretching, and you have compressing for horizontal and vertical. Then we have reflections, and then we have vertical shifts. So now we can combine all of these ideas. So take a minute, pause your video, and do example 6. Example 6 says, describe the transformations needed to construct the function g of x equals -2 times the square root of x plus 2, all of that plus 3, from the basic square root function using the order of transformations. Okay, so remember the basic function, which is mentioned, is the square root function. And remember, the square root function looks like that. Okay, that's the square root function. That's the square root of x. So now take a minute and do your shifts in this order. Okay, so let's do this in a few steps. Okay, so the square root of x plus 2, we'll do in yellow. Let's use the highlighter. The square root of x plus 2. Remember, this plus 2 is on the inside or underneath the square root, so that says we do the opposite. So if we're starting here with the square root of x, that means we need to take it and we need to move to the left 2. So let's move to the left 2. So this is the graph of the square root of x plus 2, all of that underneath the radical. And now let's use the red highlighter and examine -2 times the square root of x plus 2. -2 times the square root of x plus 2 stretches this a little bit, stretches the square root of x plus 2 vertically by 2. But that negative on the outside says we take it, the graph is our it, and we reflect it across the x-axis. So this red graph is -2 times the square root of x plus 2. And now when we add 3 to -2 times the square root of x plus 2, let's use our black highlighter for that. That means we then take our red graph here and we move up 3. Okay, because whenever you add or subtract a number on the outside of a given function, that means we do a vertical shift. Okay, so we take this red graph, move it up 3. So now we're here at our starting point. And then we sketch our graph. It'll look something like so. Okay, all right, there you go. So this concludes transformations of functions.